Hi kids, we will be going with this paper discussion. You can look at the first question. First question says the electrical circuit in the diagram consists of identical resistors with resistance R and a voltage source with a constant voltage U. The two conducting metal spheres of radius R and 2R are connected to the circuit via long wires. The resistance of the wires and the sphere can be neglected. The spheres are far away from each other and from other objects. Initially, the spheres are uncharged and both the switches are open. Mark the incorrect statement. Going with the options, potential of the spheres after equilibrium in the circuit has been reached when switch K1 is closed. Switch K1 is closed and K2 is open. So I have removed this. Now you can understand this is isolated system, so the net charge on it should be 0. So if this is plus Q, this is going to be minus Q, and this potential difference will be U. Instead of U, I am calling it as E. So potential of this is KQ by R, potential of this is minus KQ by 2R. The difference is going to be E. From there you will be getting KQ by R, and you can get minus KQ by 2R. So this potential is 2E by 3, this potential is minus E by 3. Now they were asking, now what will happen if you close this switch? If you close this switch, at this moment the potential in this is 2E by 3 and this is minus E by 3. Then you can consider it like a T-shaped figure. Outgoing current plus outgoing current plus outgoing current is 0. From there you can get this potential is E by 9, which is average of 3, or you can go with outgoing current plus outgoing current plus outgoing current is 0. That is also correct, but we need to mark incorrect options. Going to option C, K1 is kept closed for a long time and potential on the spheres after equilibrium is restored. Now after equilibrium is restored, when steady state is happening, when these were fully charged, so they were talking about the potential of this is 2U by 3 and U by 3. See, the difference always should be U, so that is obviously going to be wrong answer. So if I call this charge is X, this charge is Y, this charge is Y, at any time the potential difference will be equals to E. Now that is one equation. Now apart from that, if you take this total system, you can see this current is going to change the total charge on the system. Total charge on the system will be changing. So you can write this equation. This current will be changing the total charge. In fact, it is decreasing, right? Now apart from that, you can write for this potential, you know, Ky by 2R, this potential, you know, Kx by R. So again, by taking outgoing current plus outgoing current plus outgoing current is 0, you can get this potential. That potential is going to be this much, so that potential equals to I into R. So basically you got one equation from here, you got one equation from here, then you need to solve for it. For that I have to rely on this equation, because this is going to give me how this current is varying with the time, because I need heat in this later on, right? So from here, from these two equations, you can find what is the value of X and what is the value of Y. Once you find what is the value of X and Y, you can substitute it here. Then it looks like I dash equals to minus lambda into Y. This equation, we know this general solution is going to be this much, where I naught is initial value of that. Initial value of that was E by 9R, that you have seen in option B, right? So now you know current is varying with time. So if you want to find the heat, then it is going to be I square R dt. So you will be substituting this I value and you will be integrating. Where option D is correct, but we need to mark incorrect options. That is going to be option C. A solid conducting sphere of radius R has a cavity R0. A point charge Q is placed at the center of the cavity. A dipole having dipole moment P bar is placed outside the sphere as shown in the figure. Choose the correct statement. So the first thing is, you will be drawing a Gaussian surface here and electric field everywhere here is 0. So flux is 0. So total charge enclosed will be 0. So inside charge will be minus Q, and as it is at the center, it will be uniform distribution. Now if this is minus Q, outside charge is going to become plus Q. but dipole is there. Because of the dipole, field will be this way, so positive charges will be more accumulated here, less accumulated here. It is non-uniform. Then they were asking force on Q due to the dipole. Force on Q due to the dipole alone, it is going to be 2 kp by r cube times of Q, which is not 0. Force on this charge because of this outside pair is going to be 0. Force on Q due to the dipole is going to be 2 kp by distance cube into this much. So that is going to give you option B is correct. 2 kp by this distance cube, z plus x plus y. Then you need to prove remaining two options were wrong. Potential at point A due to the induced charges on the outer surface. Now you should understand, field because of this pair is 0 inside everywhere. So potential because of this pair is same everywhere inside, which is easy to calculate at O. So let me calculate potential at O. Potential at O due to this is going to be minus kp by this distance square. That is potential because of the dipole here, but this is non-uniform distribution. Still you can find the potential at the center, which is this much. So potential at the center because of this outside thing is going to be this much. Because of this inside thing is going to be 0. So potential of the conductor is going to be this much, you can say. So at A, potential of the conductor is this much. But if you want to find because of the induced charges, you need to subtract what is the potential due to dipole here. You are subtracting what is the potential due to dipole. So this was the potential at A, and you are subtracting potential due to dipole, which doesn't match with option C anyway. If 15 charges are to be arranged in a circular region such that the potential energy of the system is minimum, then they should be arranged as. Yeah, so I think this question can't be solved with whatever knowledge I have as of now. So I thought we can solve it without the given comprehension, but it is the given comprehension is needed. I will be attaching the given comprehension. In the comprehension, they were telling about how it varies when n is greater than 12. Till 12, you can put them on the circumference. After that, things are going to change, and the question they have given is about 15 charges. Anyway, we could have eliminated this option which doesn't look symmetrical. So out of these options, one will be correct. But for more than 12, the corresponding figures are going to be something like this. In this scenario, they were talking about 15. And if I see any better way of understanding this without high-five math, I'll attach it in the PDF by that time if I find, or else this comprehension is needed to solve the question. Two infinite long wires are having uniform linear charge density. They are parallel to z-axis and passes through x minus a and plus a, the radius of the equipotential cylinder. So you can look into given solution. Those who are good at math, those who are not really great at math, you can go with potential if everywhere is same here in this circle. I mean every plane will be symmetrical to this. So if you, instead of finding at random location, you find the potential here. You find the potential here. These two are good points. Potential here, if this distance is r, this is going to be 2a minus r. Potential here is going to be 2k lambda by r integration. It is going to be, if you take a reference as r naught, then you will be getting 2k lambda log r minus log r naught. So this is the potential because of this thing here. Due to this thing, it is going to be this much. So potential due to these two charges here is this much, which is equals to given value. And similarly, if you want to find here, that is going to be r plus 2r, and for this guy the distance is going to be 2r minus this distance. Then you need to solve for it. So I have just taken this and I found what is r in terms of a. Then I have taken these two. I have taken these two. I have taken these two only. From here, after that I substituted this value. So that is doable for you. Or if you are good at math, probably given solution is also much easy. Then in the next question, there are a couple of things. They have given potential and they ask you to find electric field. The relation between potential and electric field you already will be knowing, minus dou v by dou x I cap dou v by dou by j cap, dou u by dou z k cap, and you have to substitute the values given, which will give you P as option 4. In the next case, charge is given as varying as a function of time. From there you can find the current. Then they were asking power. They were asking maximum power, but I think for some reason for maximum first differentiation has to be 0, but here that is going to be minimum. In fact, power is going to be 0 at t equals to 1. So I don't think it is maximum what they were doing. So anyway, so if I leave it and if I go to the next parts, okay, there are a lot many things written here. I will just explain, mark one by one. So you can find the equivalent resistance. These two are parallel. So 2 by 3, 2 by 3, 4 by 3, 4 by 3 plus 1. So when you use V equals to IR, you will be getting current is 12. Current is 12. Current is 12. After that, you can see the resistors are in the ratio 1:2. So currents will be distributing in the ratio 1:2. Once you see this, if you assume this potential is 0, then this potential is going to be 8. This potential is 28, 16, all these values you will be getting. Then incoming current is 8, outgoing current is 4. So this current is going to be 4. So if you want to find current in the resistance-less wire, you should be taking help of only KCL. V equals to IR is not going to help you much here. Going to the next part, basically you need to calculate RThevenin. If you want to calculate RThevenin, you will open the load and you will short circuit the batteries and you will be calculating what is the equivalent resistance across this. This is 10, this is 10, 10 and 10 parallel, you will be getting Thevenin is 5. So you can replace all the batteries with some battery and all the resistors with this resistance, and if the power in this one has to be maximum, this resistance value should be equal to that value by maximum power transfer theorem. Let us consider 3 parallel thin metal plates of these dimensions, and they have given some information. All you need to do is redraw the figure. So battery is connected. If I take this is 0 volt, this is going to be E. Now this value I don't know, I am calling this center thing is at potential X. This center thing is at potential 0. This one I am calling it as Y. Now you can see this has no connection like capacitor plate. This is going to act like one pair. This is going to act like one pair. This is going to act like one pair. So there are some couple of capacitors. If I try to redraw the figure, the potentials here are 0, X, E and Y. 0, E, X and Y. If I draw battery is between 0 and E, and this resistor is between E and X. Between E and X there is a resistor of R. Then this capacitor is between X and 0. Between X and 0 there is a green color capacitor whose value is epsilon A by 3 by 2D. If I call epsilon A by D as C, then this is going to be C by 6. Then similarly this is between X and Y. X and Y. This is between Y and 0. Y and 0. This is between X and Y. And this resistor is between Y and this resistor is between Y and 0. This is between Y and X. Y and 0 and Y and X. Now eventually when the capacitors get charged, then they will behave like open circuits. Current will be only flowing like this. Then you can easily find the current. You can easily find the potential difference. Potential difference for the total 3 is E. So this is going to be E by 3, E by 3, E by 3. So once you get that values, I have just zoomed in so that I can show you what are the charges. Once I find the potentials, then this capacitor is between 0 and E by 3, so I can find the charge. This is between 0 and 2E by 3, so I can find the charge. Similarly, this is between E by 3 and 2E by 3, I can find the charge. Then they were asking about charge on plate 1. Charge on plate 1. Charge on top plate. Charge on the top plate. Top plate, that is whichever is connected to X. Which is connected to X here? This plate and this plate. So this charge plus this charge plus this charge. Right, so from there option A is correct. Now similarly plate 2, whichever is connected to Y, so that is this plate, this plate, this plate. So that is going to be minus CE by 9. So option B is also correct. Then charge on the bottom plate, that is whichever is connected to 0, that is this plus this, that is going to be minus 2 by 9 times of CE, which is wrong. Option C and D were wrong. A classmate modified a meter with a range of 200 microampere and internal resistance 500 ohm into dual ammeter. Okay, so they have given some information. And again, there are a couple of things here. So let me explain step by step. When the switch is set to position 1, so they said this thing and they gave this value also. From there you can calculate what is this potential, and this current is same in this also, so you can find what is this potential difference, and this current is same in this also, so you can find this potential difference. So when you go from here to here, you will understand potential difference is 2.5, that is in parallel with this. So this potential difference is also 2.5. This resistance you know, this potential difference you know, then you can calculate the current in this. You can calculate the current in this. So if this is 500 and this is 200, then this is going to be 700 micro. So basically when the current is 700 micro, it is going to show maximum deflection. So basically this is going to act like an ammeter whose range is 700 micro. So option A and B were wrong. In the next case they said it is showing something related to figure 2. In figure 2 it is 140 micro. It is reading 140 micro, so this potential difference is I into R. So similarly this one also you can calculate. Now this entire thing is in parallel with this, so potential difference is 0.14. When you divide with this total resistance, you will be getting this current. This current plus this current is going to be this current, so it is going to act like an ammeter which is measuring 980 by 3 right now, but in the deflection it will be showing 140, right? So in the next case, they have connected to a battery. If you connect lower potential here, higher potential here, if I take lower potential as 0, higher potential as V, this is between 0 and V, 0 and V, 0 and V. So if I use Q equals to CV, I will be getting this charge as positive charge, negative charge, and yeah, this capacitance is 2.5 times of volt capacitance. So the charge on this plate is going to be 2.5 CV minus 2.5 CV. But we understand the net field in this region and in this region should be same, because this distance and this distance is same, potential difference is same. So you can easily understand the net charge on here should be same as CV. So for that, this induced charge will be minus 1.5 CV. Or if you know some formulae, whatever you have learned, you can use them also. But it is quite obvious to see from here, the net charge here should be CV. Right, the same way charge here is CV. Then going to the next part, again the same idea, charge here is CV minus CV. This capacitance is 2 times, so this charge will be 2 times of CV, but the net charge should be CV, so this induced charge will be minus CV. The same goes there. Then I think you can find the answers easily from there. A gas lamp having resistance RL is connected in a circuit as shown. The resistance RL varies with voltage like this given. When the applied voltage is 0, its resistance is very high. When the applied voltage is 0, this resistance is very high. Now when you close it, this will keep charging, getting charged, and at some point of time it is going to become V by 2. Once it becomes greater than V by 2, then this value is going to change. So after that point, it is going to become very small resistance when compared to this. Then its potential is going to reduce to V by 4. Then again, it will become more. Again, it will be getting charged. So that's what is going to happen. So it will be getting charged till V by 2. After that, this resistance will be becoming small. Then it will be discharging to V by 4. Again, this resistance will be becoming large. Again, it will be charging, and it will become V by 2 and resistance will become less. So it always stays between V by 2 to V by 4 and V by 2, that you can see from this figure. And they were talking about the frequency of the flash. The flash in the sense, once it is charging to V by 2, then it will be flashing, then again it is going to V by 4, from V by 4 it will be building up to V by 2, again it will be flashing. So basically you need to calculate what is the time gap to go from V by 4 to V by 2. So after that time it will be flashing. Again, what is the time to go from V by 4 to V by 2? So we need to calculate what is the time taken to go from V by 4 to V by 2. So when it is V by 4, the scenario looks like this. This resistance is 100 times of this. right? Now it has to build up. It has to build up. Now for that I'll be calculating V Thevenin and R Thevenin. If I want to calculate V Thevenin across this, I'll open this load and I'll find what's the potential difference across this. Current in this is going to be this much into this resistance is going to give me potential difference across this. That is V Thevenin. Similarly, if I want to find R Thevenin, I'll short circuit this, I'll open this, and these two are parallel. So R Thevenin is going to be this much. That was 5K, it was not R Thevenin, that was 5K. Then if you know V Thevenin and R Thevenin, you can replace this center circuit with one voltage button, one resistor connected to this capacitor. Then we know the solution will be of this form, and at t equals to 0, potential difference across the battery is this much. When this continues like this, generally, I mean, this is a normal circuit. If you assume it's a normal circuit, at t tends to infinity, the potential difference across this is going to be this much. So when you solve for it, you will be understanding what is the value of A and B, and when you substitute it back, you will be getting how potential is varying with the time, But we need to see when it becomes V by 2. When it becomes V by 2, then it's only about substituting the values. So value substitution you can do, and it's a, I mean, if you want to roughly approximate it, you could have taken like short circuit and open circuit. When it's larger resistance, you can open circuit and you can manage. Roughly you will be getting the answer. Figure shows potentiometer circuit. The length of the potentiometer wire AB is 120 centimeter and its resistance is 2 ohm. The internal resistance of 6 volt cell is 1 ohm. Initially the switches S1 and S2 are open. So they have given couple of questions. I have drawn the figures for all of them, and given this value, we will be taking this as reference. For 120 centimeter, the resistance is 2 ohm, and when S1 is open, when only S2 is open, so when you draw the figure, see, galvanometer will be showing 0 deflection. The meaning is this circuit and this circuit will act independent of each other, and this resistance is 2, this battery is 6, this resistance is 1, so resistance is 3 and voltage is 6, so current is going to be 2, and current in this one always going to be 2. Now here similarly you can find the current is 2 by 3, then you can find the potential difference is 2 by 3 volt. So when will this show 2 by 3 volt? This current into this resistance, when it is equals to 2 by 3, what is the value of L? Rho by A you can calculate from here. So length is 20 centimeter. When it is 20 centimeter, it is going to show 0 deflection. In the next case, when only S1 is open, this difference is 2 volt. So they were asking when is the difference 2 volt, which is I into this resistance equals to 2 volts. Rho by A we already know, so length is 60 centimeter. When this length is 60 centimeter, it is going to show 2 volt. Then in the next case, when all the three switches were closed, so basically if you close this, then potential difference across this is going to become 0, but this potential difference is 2. So this is also 2, this is also 2. They were asking when will this potential difference be 2. It is same as previous question. Then in the next case, when S3 is open and S2 is also open, but S1 is closed. And if no current is flowing through the galvanometer, no current will be flowing through this resistance also. So this potential difference will be same as this potential difference, which is 2 volt. For 2 volt you need 60 centimeters, same answer as the previous one. An insulating ring of charge 2 pi lambda b, radius b is concentric with charge conducting solid sphere of radius q, charge q and radius a. Then they have given couple of options. I have straight away marked C is wrong, D is correct. Electric field inside the sphere should be 0 because it is a conductor and we are talking about static situation, and that implies it is a equipotential body, so option D is correct. Then potential of the sphere, it is hard to find at any point than the center, so we will find at the center. Potential due to the ring at the center is going to be, it's at equal distance, so it will be kq by distance, kq by radius. This is potential due to the ring. Now whatever charge on the conductor, that will be non-uniform, maybe, yeah, mostly it should be non-uniform. Whatever it is, the field everywhere should be 0 inside according to the charge distribution, and you can convince yourself by taking Gaussian surface, no charge will be inside the conductor. As it is equal distance from the center, potential at the center is going to be kq by A. Now they were saying when the sphere is grounded, charge on the sphere won't be q, it will be something, let me call it as x, but this total value should be 0. From there you can get the value of x, which doesn't match with option B, at least dimensions also. Choose the correct statement. Coulomb's law can be used to calculate force between two charges when they are at rest only. Yes, Coulomb's law is defined for static situation where the charges are at rest. Gauss law can be valid for moving charges also. Even though moving charges create induced electric field, but flux through due to induced electric field through any surface, through closed surface, will be 0, right? So I think Gauss law, when you do flux because of conservative field plus non-conservative field, this is anyway 0, so that will eventually give you charge enclosed by epsilon naught. So that is also correct. Then Kirchhoff's laws were valid in AC circuits also. That's how we build the solutions of the equations also. Two solid spheres. So then they're asking about rate of cooling dependency on the radius. So E sigma A T power 1 minus T naught power 4 will be the power lost. That will be going as rate of change of whatever temperature. I mean M minus MS dt. Now they were asking rate of cooling. How is it dependent on the radius? Area depends on the radius, like inversely proportional to r square. Mass depends on the volume. Area is proportional to r square. Mass depends on the volume, which is proportional to r cube. So rate of cooling is inversely proportional to r. So smaller the radius, more rate of cooling. So smaller one will be cooling quicker, right? So one, for better understanding, I have attached electric field lines of an oscillating point charge. Now the field lines doesn't match with whatever you will be learning from Coulomb's law, but still if you take a closed surface, still the number of field lines will be same. And I think this is already there in the doubt clearance folder, or you will have learned in the classes. Outside charges will be half of the total charge generally. So they will be equal in magnitude. So option A is wrong. Everything will be based on field inside the conducting material has to be 0. And if you ground any of the plate, total charge of the system is going to be 0. So outside charges are going to be half of the total, which is 0. So total charge was summation of all this, which became 0. So the charge flown should be that much. So option D is correct. So whatever charge is there that has flown, though I don't have a good reasoning for that, but you take it for granted. If you are grounding some plate, overall charge of the system is going to become 0. So outside charges are going to be half of the total, which is 0. So there is this question where you can read the question. The scenario is like you are connecting in one orientation first, then you are rotating. So ammeter is going to go here. You are connecting in another orientation. Ammeter's resistance is 5. Then if this EMF of the battery is E, then current in this is going to be E by 5. Current in this is going to be E by 500 plus this resistance. Similarly here, current in this is going to be E by V. Current in this is going to be E by 505. Then we need to find what is the product of potential difference across the voltmeter to current in the ammeter. Similarly, the same thing here. This potential difference across the voltmeter is this current times of this resistance, then multiply with the current in the ammeter. That is 100 given. Now in the next case, this current into this potential difference. This potential difference is nothing but E, right? That is 1. So two equations, two unknowns. Either you can take the ratio or you can find E square from there and you can substitute it here. Then solve for resistance of the voltmeter. So in this question, there are two scenarios. In the first scenario, you are closing K1 first, then this will be charged to CE. Then you are closing K2. When you close K2, then this charge CE will be redistributed as CE by 2, CE by 2. Then battery will be, this potential difference is becoming E by 2. Then battery will be supplying the charge till this becomes CE and CE. Then again, when you close it, the charge will be redistributing among these three. Again, battery will be supplying. So this is what is happening. So eventually you close 2022. So equivalent capacitance is 2022 C, or I can say this charge is CE. So total charge is 2022 CE. Now when you close this switch, as this resistances will be very small, so we'll be assuming the charges here will be redistributing very fast. So whatever charge is available on 2022 capacitors will be redistributing onto 2023 capacitors. So potential difference is going to become something now. So charge is going to redistribute. Charge which was on 2022 capacitors is redistributing onto 2023. Then the new potential difference across the capacitors is going to become this much. For easy writing, I am calling 2023 as n. This is going to be n minus 1. So then again battery will be giving some charge such that this will become Ce, 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 Ce. So new charge is NCE, old charge was n minus 1 Ce. So battery is supplying a charge of Ce. So what done by the battery is this much. Then new energies in the capacitors are going to be half Ce square, Ce square, Ce square. So it is going to become this is the new energy in the capacitors. Old energies in the capacitors when this potential difference became V was this much. This is the new energy, this is the old energy. Then the difference is going to be this much. So basically now if we neglect the amount of heat generated in the resistors whatever are here, then out of Ce square some part is missing. This is less than C square. Work done by the battery is C square, but energy stored in the capacitors is this much less than C square, so that it will be going as heat. In the second case it was pretty easy. You are closing all this first, so nothing is going to happen till you close this. Once you close this, these capacitors are they are parallel, so it is going to become 2023 C. So charge given by the battery you can calculate easily, that is 2023 Ce times of E gives you work done by the battery. Now energy stored in the capacitors, now you can see half of it will be going as heat. Then you should take the ratio of these two heats, which is going to be n square 2023 square. So answer is going to be 2023. The electric circuit shown in the diagram consists of ideal source of constant voltage, ideal ammeter with R1 plus R2 is constant. Determine the value of R2 by R1 such that I is minimum. So if I assume this potential is 0, this is going to be E, this is going to be 0. I can see a T shape here. So if I assume this potential is X, outgoing current plus outgoing current plus outgoing current should be equals to 0. From there I will get this potential. If I get this potential, if I want to find this current, then I need to divide with, I need to find this current. So I need to divide with R2. So once I divide with R2, I will be getting this expression. From this expression, as I know R1 plus R2 is constant, if I take R3 common, that constant I am calling it as R. So basically there is only R1 into R2 together, remaining all things were constants, but we know R1 plus R2 is a fixed quantity. If sum is fixed and if you want to find the maximum value of the product such that current is going to become minimum, maximum value of the product will happen, that is AM greater than or equals to GM you can use, or maximum will happen when R1 equals to R2, right? I think this kind of question we have already seen many times. So after integration, it is going to look like charge density here times flux because of this. Charge density here times flux because of this. As the flux depends on the angle and the angle is same both the places, then force on this will be same as force on this. So the net force is going to be 0. I have attached the PDF below where we have talked about how to find the force like by this point charge on this plate. And they were asking you to take the ratio of something, and that also you would have seen in the PDF. So if there were two charges A and B, then the field at some location is going to become this much. So if I want to calculate what is the energy stored, half epsilon naught E square is energy density times any volume. If I integrate it, I will be getting the total energy. If I expand it, I will be getting three terms. If you look at this term looks like only field because of A or energy because of A, that is self energy. Self energy of A is going to be kq square by 2 times of its radius. Similarly, this expression is going to be self energy of B, which is k q square by 2r, and this is interaction energy. Interaction energy is potential because of this here into charge of this, that is kq by 4r times of q. And I think they were asking the ratio of these two or something like that, so that you can manage from here. So in this question, so you will be taking Gaussian surface here, flux will be 0, so total charge enclosed will be 0, whatever charge given that will go here. The same argument will go here, and you can say this is minus 3q, total charge is 6, minus 3 is here, so here it will be 9. If this is 9, this will be minus 9 by Gauss law, and total charge is minus 9. Total charge is minus 9, and that is minus 9. So this will be 0. If this is 0, this is 0. You can do that by Gauss law. So total charge will be outside. This is how it looks initially. Now later on you are closing the switch S1. When you close the switch S1, again by the same argument I can say this is 0, 3q minus 3q, 9q minus 9q, but this is grounded, so I don't know what is this charge. If this is x, this is minus x. If this is minus x, this is 12q plus x. But we know this potential is 0. Potential because of this field, because of this pair, and potential is 0 outside. Field because of this pair and potential is 0 outside, so I don't have to really care. Potential because of this is this much. Potential because of this charge inside is this much. But potential because of this charge plus this charge should be 0. From there you will be getting the value of this is minus 9q. Minus 9q. Earlier total charge on this is minus 9q. Now it is minus 18q. Whichever was 0, now it became minus q. So the charge flown is 9q magnitude wise. It minus 9q flown from the ground. Then you can go by the same argument here, or you can quickly see if these two are grounded, basically it is like wire joined from here to here. So if a wire is joined from here to here, this 9q minus 9q will disappear. So that's how it is going to look like. So if that disappears, so what is the charge flown? Charge flown 9q flown into the ground. 9q has flown into the ground. So they are asking the ratio of them, which is 1. So in the next question, a hollow non-conducting sphere of radius a and solid non-conducting sphere of radius a, charge q1 minus 2q. They are asking the ratio of kinetic energy. So I don't think this question has something to do with electrostatics other than understanding the forces for internal forces. There are internal forces and it is pure rolling, so there will be friction also. So if I take torque about this point, torque due to mg normal will be getting cancelled and torque due to internal forces will be 0. Torque due to friction is also going to be 0. So I can do conservation of angular momentum about this. So angular momentum of this is going to be this much about this point, off center of mass and about center of mass together. Similarly for this one is going to be this much. Angular momentum should be 0. So magnitude of this should be equals to this. From there you will be getting, they have a unique relation of the ratios. Then they were asking kinetic energy ratio. So if I say this kinetic energy is eta times of this kinetic energy, this is translational plus rotational. Then we are getting this eta, but they asked 100 eta in the question. So we'll be borrowing this result and we'll be using it there. So the main thing is, while taking the ratio, you will understand it depends on the velocities ratio. Velocities ratio can be uniquely determined by conservation of angular momentum about point P. Right? Thank you.